Good afternoon, everyone. My name is Ms. Gomez, your science teacher, just in case you've forgotten about me. I just wanted to make a really quick video about kind of what we had to skip over and basically what you just read last week from the series books. I just wanted to give a really quick, you know, video. I don't know, just a really quick lesson for you to, if you didn't understand the reading, then maybe you'll be able to understand it through here. Okay, so just like anything, there's a life cycle to anything. It has a beginning and it will have an end. Same thing with our star, who is the closest one, is the sun, right? Now, where does the sun fall under? Yes, it's massive, but guess what, guys? There's other stars that are much, much more bigger than the sun. Okay, so where do they all start from? They all start from what you see right here. It's called a stellar nebula. So imagine just all of that being gas and dust. Because of gravity, they start, attracting to each other and they start coming together. Now, it has two options. It has the option of becoming an average star. When there's not too much gas, too much dust, all of this dust just and gas start to clump together and it'll form an average star. Most of your stars are average, and that's what our sun is at right now. He is a main sequence star. So sometimes we call it average star and sometimes we call it main sequence stars, which we'll be going back to in just a second. Now, what happens is that in our sun right now, it's mainly composed of hydrogen, and this hydrogen is going through so much energy right now. Is burning through so much energy that it starts to fuse. Um, and when two hydrogen atoms start to fuse together, it starts to become helium. So it's kind of like, okay, all of this hydrogen atoms fusing together and it starts producing helium. Now, over in millions and millions of years, guys, it'll start becoming a red giant. So all of this hydrogen is being formed into helium, and helium is a bigger atom than hydrogen. So what starts to happen is that the size of this star starts to grow bigger. So eventually, guys, our sun is going to become, instead of an average star, what it is right now, it's going to start expanding basically, and it's going to start becoming a red giant. Now, from there, it has the option of once it runs out of hydrogen to fuse, then there's just helium, and the helium will just stay there, and then boop, it'll just kind of like pop. It won't pop to like a major explosion compared to, again, other types of stars that pop. It'll just become a planetary nebula. And if you notice, that's exactly the same word from here. So planetary nebula is basically where this red giant it didn't have any more energy, any more fuel to keep on fusing. So then it just pops, and all of the rest of the gas that was outside of the star just drifts off into space. And then anything that's right here will eventually become a white dwarf. So when you see a white dwarf, that's when you know, okay, that's the end of the star's life. That's basically it. And then all of this gas that, went into space, well, maybe later on it could be coming back to another stellar nebula. Sorry. Okay, so that one's that. Let me move this little thingy. Okay, now let's talk about other stars. And this is very few stars actually that become red supergiants and so on. Okay, so if there's enough gas, if there's enough dust, then it'll become a massive star. Okay, this massive stars usually are about 100 times bigger than the sun. That's what we know of so far. And again, it's the same thing. After millions and millions of years, this hydrogen there's not enough hydrogen to fuse together, so then it becomes helium. And like I said, helium is a little bit of a bigger atom than the massive star, so then it'll just become a red supergiant. So again, our sun is never going to become a red supergiant. Millions and millions of years later, guys, it's going to become a red giant. But as of a massive star, that's when it becomes a red supergiant. Now, because it's so massive, this will pretty much explode into a supernova. So what happens is that all of this energy just doesn't know where to go anymore, and so it collapses back inside. And then when that happens, all of this energy just begins to flow it out into space, basically. And there's better pictures about supernovas. I mean, it would look like, let me see if I can find it again. I'll show you right now all of those. But a red supernova, not a red. It can be like this one in the middle. Okay, that's what we normally see in when we look through telescopes and we look into the universe. If we see this, we're like, oh, okay, it's because a red supergiant, is at the end phase of its life. Okay. All right, and then from there it has two options. Most of the time, guys, a supernova will become a neutron star. And all a neutron star is, it's a very small star. And every time you see a neutron star, and then you'll know, okay, that was the end of a massive star's life. And a neutron star, just like it says right here, these may be produced after a supernova explosion. They are small and have faint light luminosity. They don't have as much luminosity as other stars, so they cannot be seen with the naked eye. So what would we use? Going back to the electromagnetic spectrum, we would then use other wavelengths such as gamma, X-rays, and infrared. Okay, satellites. Now, very, very few of, can't find my mouse. There you go. Okay, very few of these massive stars. Very, very, very few, guys, of them. When they explode, it just depends on the circumstances. Then instead of becoming a neutron star, it'll become a black hole. Okay, and if we go back over here, what is a black hole? So a black hole is if an object greater than 4 times the sun is left after supernova, it will become a black hole. The gravitational pull is so great, not even light can escape it. Okay, so that's why it's called a black hole. So basically, the black hole would be this at the center, and that's why this isn't a galaxy. Okay, but most galaxies, they do have a black hole in the middle, because then it has so much gravitational pull that it's just pulling it all inside, and not even light can escape it. And like I had mentioned before we had left, we don't know where it goes to. So maybe your future generations will be able to figure that out. Okay, so this was like 2 days of activities that I had planned, but well, that couldn't be done. Okay, so one more thing that I wanted to tell you. Okay, let me see. This is the first time I'm. Oh, that's an eraser. Let me zoom out. No, okay. So what I wanted to show you actually was this. Okay, basically this is what you saw on the benchmark. This is only one example of how you would see a HR diagram. What is an HR diagram? An HR diagram is just a graph that these two scientists, Hertzsprung and Russell, put together, and it's just a graph, pretty much grouping all of the stars, and they fit into these categories. Okay, so what categories do you have? They all have something in common, guys. Okay, just like a normal graph, you have your y-axis, and usually your y-axis is going to be charting how bright it is, its luminosity. Okay, so here it's referencing to the luminosity of a sun. Okay, so anything from here above is much, much brighter than the sun, up to 2 to the second power, up to 10, I'm sorry, 10 to the second power, after 10 to the fourth power, and 10 to the sixth power. And if you guys just put that 10 to the sixth power, what does that mean? That means that it is 1 million times brighter than the sun. Okay, so let's go back to the HR diagram. So that means that anything that's up here, ladies and gentlemen, it is much, much brighter than the sun. Okay, now, and then down here, I want you to notice this part. This is very important because you're gonna see. Okay, if you notice, the temperature here changes. It's not like your normal graphs that you see in math. Instead of seeing a 0 over here, what do we see? The highest temperature, right? And instead of seeing the highest number over here, what do we have? The lowest temperature. So the HR diagram, because of how it's grouped, they decided to put the numbers increasing from right to left. So think of your coldest star, starting from here, and then it starts increasing in temperature as you go to the left side. Okay, so that's the only difference here with the normal graph. And as you notice, your temperature isn't measured in Celsius and Fahrenheit. Why? Because stars are so hot that we couldn't measure. Well, we can measure, but it wouldn't be the best data that we can get if we just use Fahrenheit and Celsius. It would be too big of a number. So what do we use? Usually, guys, in science and chemistry, you're gonna see the letter K. The letter K stands for Kelvin. Okay, this is only used for stuff that is like exceeds the normal amount of temperatures from Fahrenheit and Celsius. So instead of using Fahrenheit and Celsius, we use Kelvin, which is, a step higher, and they're so much hotter. So even though here, think about it, guys, it's 2500 Kelvin. Just so you have an idea of what that is, let's just put it into the Google. What's 2500 Kelvin in Fahrenheit, since that's what we know? Guys, Fahrenheit 2500 Kelvin is 4040 degrees Fahrenheit. Is that pretty hot? I would say so. So, and imagine what happens once you get farther and farther and farther towards the origin. But instead of it being 0, guys, the number increases, which means that these are your hottest stars. What do you notice? Look at the colors. Okay? Look at the colors. Your coolest stars are red and yellow, yet your hottest stars are blue. Okay? So, what can you see? I just want you to think about that. Every time in stars, guys, in stars, instead of thinking of red as being the hottest of the hottest, guess what? In stars, it's the total opposite. If they're blue, if they're white, that means that they are extremely hot. Just like when you light a match, okay? When you light a match, the very tip of the match, it's blue, right? And then the top of the flame is red. Why? Because the tip of the match is much hotter, just like in stars. Okay? So, where have we seen these words before? Red supergiants, red giants, main sequence, white dwarfs, main sequence, blue giants. We saw them when we were talking about the life cycle of a star. They have something in common. Okay? They have something in common. When it's a white dwarf, which means it was at the end of a star's life. Which star's life? If we go back, a white dwarf is when it was the end of a average star's life. So basically, our sun is going to become at the end of its life a white dwarf. And what are the characteristics of a white dwarf? Well, it's extremely hot, very, very hot, but look at its luminosity. It's less than 1. Remember, what was 1? 1 is how bright the sun is. So if it's 10 to the negative second power, again, let's just put that in the, use what you have, guys. 10 to the, how do I put negative second power? Let's see what it says. So that means that it's 0.01 of the brightness of a sun. So is that less or is that more? It's much less, guys. So white dwarfs are they're gonna be dull. Their luminosity is not going to be as bright. Okay. All right. So here we have a whole group called main sequence. if you remember, go back over here. Another word for an average star is main sequence. So all of this group right here is called a main sequence stars. That's what most of your stars become. Okay, they're just average size. That's all that means. That it's just an average star. Okay, and most of the stars fall under that category. That's why they're called main sequence or average star. Okay. All right. And then obviously we have our red giants. Our red giants can be yellow in color. It can be like a tan color. Some of them are orange. But again, if they're more orange, that means that they're cooler than your whiter, tanner stars. Then from a red giant, again, where does this follow? Okay, going back to the life cycle of a star. A red giant is when that hydrogen is running out, right? So it's becoming helium mostly. So you have a red giant right there after an average star, which is our sun. Our sun is eventually going to become a red giant. So where is that going to fall under? Right here. So the sun, after a while, is going to start falling in this category, a red giant. Okay. Could the sun ever become a red supergiant? No. Why? Because it's not a massive star. Okay. And then we have two types of giants. We have red giants and we have blue giants. What's the difference between the two? Red giants are cooler and less bright than blue giants. Blue giants are hotter. Do you notice that number? And a lot more brighter. Okay, they're up there. Okay, and then you have your red supergiants, which obviously this red supergiant is, you remember, go back to red supergiant. This is when a massive star is starting to expand. Okay, and what happens? It's a lot cooler. That's it. Okay, so where does our sun fall under? Our sun actually falls under one around this area. Okay, our sun is considered an average star and it still has a long way to go. Okay, so don't worry about extinction because of the sun exploding on us, because it won't happen in our lifetime, guys. um it's gonna stay as an average star for millions and millions and millions of years. The our star the sun still has about 10 billion years of life, so don't worry about that. Okay, so I know this was a very long video, but I just wanted to you know show you about the life cycle of a star, and basically this is all crunched together into a bunch of activities that I had planned for you. But so make sure to do the green book. Now we're into a new unit, and just keep updated in the announcements for Google Classroom. Any questions that you have for me, please feel free to email me. Okay, my email is mgomez@seisd.net. See you guys. Bye.